Hi, welcome to Industrial Networking Basics, a series of progressive network design considerations. This series covers networking basics, not so basics, best practices, useful industry networking trends and technologies that every automation professional should be aware of. In today's fourth presentation in the Progressive Network Design Consideration series, we'll be talking about segmentation, what it is, why one should use it, and what some of segmenting's best practices are. But first, let's recap where we last left off with our virtual plant floor. We've laid out our individual production lines in their own individual fault-tolerant rings, knowing that we'd want to isolate the overwhelming majority of the machine's traffic to its respective production line. This not only massively reduces the amount of traffic on the rest of the network, but it also creates a significant degree of security, such as when a workstation that is connected to a palletizer in the packaging area is infected with malware. We've then also laid out our plant backbone and redundantly coupled it to the individual production line rings, knowing that we'd segment these out once we learned what segmentation is and how it worked. And this brings us to today's presentation. So why segment? Why complicate a perfectly good, wide-open network where all devices can communicate amongst themselves? And what is this all about? Should I even consider this? Well, while not applicable for most standalone applications, it should be considered for all other network applications because it can help manage, isolate traffic, increase network performance, contain network issues, control visitor access, and provide a good overall level of security. But it does require a degree of due diligence and managed switches, and possibly even a layer 3 switch for larger applications and networks. But more on that in a few slides. So where to start? Well, we've already pretty much identified those areas that have devices that need to potentially talk amongst each other. These are all in the same general physical area and are performing similar tasks. So in our case, we have the blending and mixing line, a filling line, an assembly line, and a packaging area. We then also have the engineering offices and 2 warehouse spaces. As we've laid out our networks, we'll assume that each of these areas will almost exclusively be communicating within their area and application. So assuming this, one can perceive these as virtually isolated or segmented networks. So how do we keep the traffic within these individual areas? The most commonly adopted segmenting methods used are either via IP address subnetting, VLANs, and or through the use of routers and layer 3 switches. Looking at option 1, segmenting via the use of subnetting, is effectively the use of IP addresses and their inability of communicating across subnets, meaning that devices only communicate to other devices in their same subnet. In our example on the right, only devices in subnet A, all those in the .10 subnet, can communicate amongst each other. And despite being in the same physical layer 2 network, they cannot communicate with devices in subnet B, or the .20 subnet. While all of this may appear functional on the surface, especially when tested using a simple ping command, which is unicast or one-to-one communication, one needs to understand that broadcast traffic, which is one-to-all traffic, is subnet agnostic, and that broadcast traffic will cross subnets. Examples of this are ARP, NetBIOS, DHCP, and most discovery protocols from printers, and even malware, which uses broadcast traffic to explore and propagate. The same applies to any unfiltered multicasts that then flood the network, effectively behaving like broadcast traffic. It is because of this that subnetting alone as a solution for segmentation gets a failing grade. For option 2, we have segmentation using VLANs, which are effectively virtual local area networks and hence the name. VLANs can be assigned by port, which is the most commonly used method in industrial applications, or by the device's MAC address, or even by protocol. As you can imagine, good cabling practice and documentation is imperative when using port-based VLANs. By using port-based VLANs, it allows a user to put any Ethernet-enabled device and thus its communication, into its own virtual LAN or VLAN. In the example, all devices connected to ports designated as VLAN 10 can communicate amongst themselves, and only amongst themselves. The same applies for all devices connected to ports designated as VLAN 20. Broadcasts and multicasts cannot cross VLANs in a layer 2 network. And obviously these port designations can be anywhere on the network, as long as the respective VLAN tags are preserved or tagged from one switch to the next across the network. So in terms of effectiveness, VLANs rate 7 out of 10 for small networks, but only a 3 out of 10 for large networks. So why is that? Well, segmenting just by using VLANs is typically not suited for larger networks due to the increased likelihood for needed multi-VLAN access and or inter-VLAN traffic for servers, PLCs, and HMIs, meaning that one or more devices may need to access one or more devices in another VLAN, such as a historian server. One means of permitting this is to use what is referred to as an overlapping VLAN. In this instance, devices on VLAN 30 have access to both devices on VLAN 10 as well as VLAN 20. Yet VLAN 10 and 20 are still virtually separated and the devices cannot see each other. And while effective, the use of overlapping VLANs is not recommended due to the configuration's complexity and the fact that it vastly increases with the network size, often resulting in a lack of oversight and mismanagement. Additionally, the network size in combination with the overlapping VLANs also creates unnecessary strain on the switch's processor. So, the solution? This is where we start looking at inter-VLAN routing. Inter-VLAN routing combines subnet and VLAN segmentation with layer 3, or routing. As we know, by default, devices within a subnet and a common VLAN can communicate amongst themselves, such as the .10 devices in VLAN 10 and the .20 devices in VLAN 20. If any of the devices need to communicate with the server or potentially others in another subnet, that traffic also by default is passed on to the gateway. In this case, the layer 3 switch that is doing the routing, which then passes the traffic onto the corresponding device in the other network. And because inter-VLAN routing now has given a device the ability to communicate with any other device on any other subnet, we now need to deploy some security rules and measures to keep the traffic isolated, which is easiest done in the form of ACLs or access control lists. These ACLs are very similar to a series of firewall rules that would allow a user to permit or deny any traffic by IP address, MAC address, physical port, ephemeral port, which is the protocol, whether it's TCP or UDP, and a variety of other factors, even the time of day. In the above, we would allow the 4 VLAN 30 devices on subnet A and B to communicate with the server, and with each other, or not. The granularity really is up to the application and the application's security needs. So while this fulfills our network layout and communication needs, you can see that the networks can get rather sizable, connecting thousands of devices. But where does that leave all of the IP addressing for all of these thousands of devices? And more specifically, our lack of available IP addresses for all of these devices. Next, we're going to look at one option of creating cookie cutter machines where each machine's PLC, HMI, drives, and all of the other devices have the same IP addressing scheme as those of the machine next to it. Yes, we're going to be talking about NATing, or Network Address Translation, in our next Progressive Network Design Consideration Series video. I hope you'll join us then. Thanks for watching.